Assalamualaikum dan salam sejahtera. We are going to talk about a monostable multivibrator. A monostable multivibrator circuit can be constructed using a 5 timer and one external resistor R1, two capacitors C1 and C2. You have a trigger input at pin 2 and the output is at pin 3. Whenever there is a trigger at the input, then only you have an output. So that's why the circuit is also named as one shot. There will be an output whenever you have a trigger input. Otherwise, the output will stay at a stable state. This is the operation of the circuit. You can read this later. Now I want to talk about what will happen when there is a trigger and when there is no trigger at pin 2. Basically, the monostable circuit will be stable at 0 output, meaning that at 0 volt you have a stable state. Your output of RS flip-flop Q will be at 0. This is the stable state. So, when you power up your circuit, initially your capacitor C1 will be uncharged, meaning that VC across this capacitor is 0. And the stable state is happening when there is no trigger voltage is applied. For pin 6, since it is connected to capacitor C1, the voltage here is 0 volt. For the upper comparator, the terminal negative over here will have a 2/3 of VCC, and this value is being compared with pin 6. If you see over here, this is 2/3 of VCC. It is much bigger than 0 volt at pin 6, so that's why V minus is greater than V plus. So the output comparator A will be 0, meaning that R will receive a logic 0 over here. And for the lower comparator, at the positive terminal, it is 1/3 of VCC, the voltage over here. And this voltage is being compared with the input at pin 2, the trigger voltage. When there is no trigger, meaning that at pin 2, the voltage VT at pin 2 is greater than 1/3 of VCC. We must make sure that this pin will have a voltage of greater than 1/3 of VCC if there is no trigger input is applied. So when you compare 1/3 of VCC with voltage at pin 2, which is greater than 1/3 of VCC, we say that for this particular circuit, V minus greater than V plus. When V minus greater than V plus, set receive 0. Okay, since R0 set 0, initially the output is 0. So since R0 set 0, Q will hold the previous output. So your output over here will remain at 0. When Q is 0, your Q bar will be 1. And when Q bar is 1, this particular transistor will on, since this is more positive than ground over here. So at this moment, the capacitor will be remain uncharged, because if this transistor is on, there is a path from this node to pin 7 to the ground, meaning that from VCC there is a current flow through R1 right to the pin 7 to the ground. So the capacitor won't be charged. Now, since this is uncharged, this is whenever there is no trigger voltage, meaning that pin 2 is at a very high voltage, which is greater than 1/3 of VCC. Q remain at stable state, which is 0. Then Q bar is 1. Your transistor is on. Pin 6 still 0, since it is connected to pin 6 is connected to capacitor C1. Okay, it is still being compared with 2 VCC over 3. Okay, over here. So if you look here, 2 VCC is greater than pin 0, V minus greater than V plus. So reset will have logic 0. For the lower comparator, the positive terminal is at 1/3 of VCC, the voltage at positive terminal. Now, when we trigger a voltage at pin 2, this trigger voltage must be less than 1/3 of VCC. And this value is being compared with this one, since VCC is greater than V minus. Okay, so this is the condition. This is the trigger voltage. It must be less than 1/3 of VCC over here. Okay, indicated by this waveform. So we have a V plus greater than V minus. 1/3 of VCC is greater than less 1/3 of VCC, your trigger voltage. Okay, so set will receive a logic 1. When set 1 reset 0, your output here will be changed to 1. Okay, you have a 1 output here, and Q bar will be 0. Okay, and this transistor will off. Once the transistor is off, there is no path from this node to pin 7 to the ground. So at this moment, capacitor will be charged through R1. Okay, so this is the unstable state. Whenever you trigger the voltage at pin 2, over here you trigger this, you will be at unstable state, and this will remain for a certain time. Okay, that is the amount of time taken to charge your capacitor over here through R1. Okay, so if we look at the capacitor, the voltage over here will be increased over the time. Okay, it should reach the maximum VCC since the power supply is VCC, but we can have only about 2/3 of VCC since this capacitor at pin 6 is being compared with this node, which is 2/3 of VCC. So the moment the voltage of the capacitor is greater than 2/3 of VCC, the upper comparator over here, V plus will greater than V minus. Since V plus over here, okay, greater than 2/3 of VCC, your V plus is greater than V minus, reset R, receive 1. And for the lower comparator over here, this is VCC over 3, and VT right now is high. Okay, so we compare these two, 1/3 of VCC with a high voltage. Okay, so it is V minus greater than V plus. Why is it VT is high? Because you trigger only for a short time. Once you trigger, it will goes back to a high state. So that's why your VT is high, and it is greater than VCC over 3. So V minus greater than V plus, so set will receive 0. When set 0, reset is 1, your Q will be back to 0. So you have a 0 output again, which is back to the stable state. The unstable is just for a short period when you're charging your capacitor just now. Okay, when Q is 0, your Q bar will be having a voltage of logic 1. So meaning that this transistor will on again. When this transistor is on, okay, the capacitor will be discharging its value through pin 7 through pin 7 to the ground. So meaning that right here, your capacitor will discharge all its voltage. Okay, the amount taken, which is T, is equivalent to the time taken for the capacitor being charged from 0 until 2/3 of VCC. Okay, so this is the time taken, and your time constant will be R1 C1, because just now we charged the capacitor through R1. Okay, this is the operation concept. And to find the time T just now, we use the equation for the capacitor. VC at any time T will equals to VC at infinity plus VC at 0 minus VC infinity multiplied with e to the minus t over tau. Okay, this is your T from 0 until 2/3 of VCC. Okay, tau just now is R1 C1, the charging constant. VC at any time T, the voltage over here is 2/3 of VCC, which is this voltage. Okay, VC at 0, the initial value, of course it is 0. And if we let the capacitor charging, it will reach maximum VCC. This is the steady state value. Plug in into the equation and solve for T. Okay, so this is we just manipulate the equation, simplify the equation, and you'll have that T equals to tau natural log of 3. Okay, or natural log of 3 is 1.1. So your time taken for the output to be high is 1.1 R1 C1. Okay, this is the time for unstable state during the high state. Okay, so it is in second, R1 and C1 is in ohms and farad respectively. Okay, so this is for the monostable multivibrator. Thank you.